Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. Today we are in a very special occasion and very special location. Hi, Bess, how are you? Bess, you're mute.
Yes, I see that. How are you, Frank? I'm good.
So Bess and I, we are going to... Good morning, good afternoon, good evening, wherever you are on this.
And Frank's got an echo going, so they have to fix the sound so that you don't hear.
Okay, we're good. Now we're good. Okay, so Bess, so we are going to talk about the Perseverance landing today, the Mars 2020 landing, to be more accurate. We are going to, we have invited, in fact, a large number of researchers, scientists, engineers, who are going to tell us first, for the first half hour, 45 minutes, their work and their contribution to the mission. And then we are going to watch together the landing and support the mission. Bess.
That's right, we'll switch to the NASA stream once we get a little bit closer to the cruise stage separation, which happens in about an hour and 10 minutes or so.
Okay, so what can we say first? Well, after 7 months journey through space, the mission is going to land on Mars. And this is going to basically be 7 minutes of terrors at its core, 7 minutes for which the mission will land on the surface of Mars. It's gonna land in a very interesting place called the Jezero crater. And we are going to talk about that with Janice Bishop. And then we are going to talk about how we engineers and scientists operate a rover and learn from data whether or not there is life on Mars. That's kind of the goal, right? I very simplify here. Okay.
We'll get into the more technical details of everything as we go.
Yeah. Let's welcome our first speaker. So I'm multitasking with different screen. Hi, Adrian.
Hi, Frank. It's fantastic.
So, Adrian,
hi, Adrian.
Fantastic day.
Good to see you again.
So maybe
Adrian.
we should introduce Adrian first. So Adrian sent me a very long bio. I know Adrian, so that's why I'm very... So Adrian is a deputy scientist for the NASA Mars 2020 rover mission. He works at the NASA headquarters. He's part of the international science team, which is currently preparing for the mission after landing. So he participated to a large number of documentaries and missions to understand the sample return. He has participated to the landing site selection for this mission. And you really sent me a very long bio. And Adrian is from Australia. So that's why he has this very interesting accent. So let's hear Adrian. And please, Adrian, tell us about the Mars 2020 mission and the NASA contribution.
G'day, Frank. Thanks for having me on board. And I'm just so happy that everyone can join us here on the SETI Live venue. So yeah, I have my task of giving everyone a little bit of an overview of the mission. Basically, Mars 2020, as Frank mentioned, is about to land in just less than 2 hours now. It's going to do that totally autonomously. That's the most stressful thing about my job, I guess, because I'm a scientist on the mission, so I don't get to play with the rover until the engineers are completely happy that the rover is functioning properly and that everything is working okay. So it's a little bit like, you know, taking out your dad's car for a drive. The engineers want to make sure that everything's working properly before the scientists get to touch it. All right, so basically as part of our mission, a major part of our mission is the fact that we'll be collecting samples, 30 samples for the Mars sample return mission, which will be launched in 2026. So we have a real drumbeat about our mission that it makes it completely different from any other Mars mission before or any other planetary mission, because we've got to be there at a specific date in a couple of years. We've got to get 30 of the best samples that we can find at Jezero Crater and then drop them off. And we're going to do that at a particular location. So we're meeting the Sample Fetch Rover, which doesn't have a cool name yet, like Perseverance, but I'm sure it will be given a cool name soon. And so that's a little bit like, we have a date with we're taking Dad's car out for a date, but he's made sure that we have to be there at 2 a.m. and he is going to meet us at this particular location. Otherwise, when just, the mission is screwed. So basically, that's the drama of this mission. Of course, there's also a lot of drama about how we're getting down onto the surface of Mars as well. That's totally autonomous. And we call it the 7 minutes of terror because we were sent to Mars at such a high speed and we have to do all this deceleration. We use all the tools in the book. We use a massive parachute to slow us down through the atmosphere. And even then, we can't slow it down quite enough. We need to use retro rockets to fire us down and burn off all that speed. And so our 1-ton rover gets lowered down onto the surface, and then the rope gets cut a lot like this scene that you're seeing right now. And hopefully the rocket flies away from the landed rover and everything goes very well. So basically the rover will then be giving us an immediate signal on its success, and we'll be sending back an immediate image from the surface. That's not going to come from, say, the Mars cam, because the Mars cam will still not be deployed at the first time. But we have small cameras called the engineering cameras. They'll be taking shots of the surroundings and telling us where we've landed on the surface. So we also have a very good knowledge of the landing site. If I could just tell you a little bit about how cool that is. So over here, we may get some images of what's called a delta. This is the delta as it appears in this animation, but actually, we're not sure if we'll actually be able to see it from our landing site, but it would be very cool if our first images were able to show us the crater edge or the delta. And the delta is really super cool because here on Earth, we know when deltas are formed, there must have been liquid water present. Okay, but that's a scientific conundrum because what's happened to that liquid water? There's no liquid water. We've been searching for liquid water on Mars. We haven't found any liquid water on the surface of Mars. So hopefully the landing site with its delta will be able to tell us a lot about how that water disappeared and whether that water was around for a long time. Was it millions of years or was it just thousands of years? Some people have said it's just brief outflows that could have caused this delta to form. So we'll be able to answer that question. And one way we'll be able to answer that is by taking the samples. And so some of our 30 samples will be of that delta. We'll be taking samples at the bottom, and also we'll be traversing going up to the top and collecting the rocks at the top and bottom. We'll then be able to send those rocks back in our Mars sample return and date those rocks. So we'll be able to immediately get a really good number on how long water was present on Mars, or in this location at any rate, and how long ago that was. And also, of course, the most exciting thing as far as I'm concerned is the possibility of finding biosignatures. And I know a lot of your SETI audience will be all over biosignatures, but for those who might not be swept up on them, biosignatures are signs of past life on the planet Mars. So if we're able to find those, I'll allow myself a moment of geek here. That would be just a singularity moment for everybody, because we would be answering the question of whether we're alone or not. And if the answer turns out to be yes on Mars, well, Perseverance could be the instrument that tells us the answer to that question. So that's an overview of the rover. I have
a question for you,
the
Adrian.
Helicopter also that we carry on board the rover and is currently slung underneath the rover is actually it's called Ingenuity, And that's actually going to be the first thing that's in operation on Mars. So basically, we're going to do all of the helicopter operations in about the April or May timeframe. And so the helicopter gets through all of its operations, and it's going to be fantastic because the helicopter has this has a really cool cameras, 2 cameras on board it. So as it flies around, it'll be able to take images of the surface, and we'll be able to get another really novel perspective on the geology around it. So I'm actually, as well as being a scientist, I'm a pilot, and as part of my PhD research in Australia, I was able to fly over the evidence of the oldest rocks on Earth and take images as well. So I know from that personal experience, the sort of the insight that you get from looking at these type of at the geology, and everybody who has had in our pre-COVID world a flight over the US said, and if you looked out your window and maybe spotted some cool rocks and thought, well, what are they about? I had that experience all the time too. And those, I mean, it just gives you an immediate insight into how much more information we'll be able to get out of that helicopter and Perseverance as a team. So both will be taking photos of each other, doing operations. We'll also be taking photos of the helicopter as it takes off, does its flights, kicks up some dust as well, and does a whole series of practice stuff for the first time on another planet. So I find that to be super cool.
So Adrian, how high is the helicopter capable of flying?
Right. So we don't have a firm number on that. And in fact, as far as the engineers are going, we are planning for 5 flights, and about maybe 100 feet might be its highest altitude. So that would probably be that's not quite a legal altitude here on Earth, but we don't have to worry about legalities or drone right of way on Mars. We don't have much competition on the surface as yet. Of course, that's with a wink and a smile. That's going to change when the Chinese arrive later on in land in Utopia Planitia. Although we won't be able to see them this time around, but yes, Perseverance will have some company.
Nice, Frank. You
So
had a
how long
question?
this spacecraft is going to last to hide on the surface of Mars?
Sorry,
sorry.
How long is it going to be in operation?
Yeah.
Right. So this box behind me, just here, this is the nuclear power source in there. So this nuclear power source is the same. It's the same type of source. It's a MMRTG source that is used by Curiosity. So that means that we have a finite lifetime, but it's a very long lifetime as far as power goes. So we will have at least 30 years power, effective power. Of course, that dies off like an exponential curve. So things start aging things have already started aging for the MMRTG. But basically, our best, the time when we need to be most effective on the surface is the first 5 years when we're collecting those 30 samples. We'll be doing a lot of high pressure activities and moving very quickly relative to other rovers, for example, but moving very quickly to our location where we'll be laying down the sample cache, which will be at the outlet channel at the inlet channel of the fluvial delta system before we exit the crater.
So Adrian, are you nervous? Are you what's your emotional state right now? Nervous, excited, a mix of everything, terrified? How you feel?
Yes, yes to all. I am super excited about today. It's been a long time coming. So I've been working personally on this for 5 years, and then There's others who've been working on the project for 8 years. It was conceived and the first instruments were chosen in 2013. So that's been a long time to develop this. And we've been looking forward to this day for all of that time. So that's it. To say I'm excited is, yeah, that's a delicious understatement, I would say, Beth.
Do you have your peanuts?
So, yeah, you have your peanuts?
I think there's still, it's snowing outside, and I think they've been snowed down.
You work at NASA, you don't have your peanuts, so we're gonna have to do something. We're gonna send you some peanuts. You have literally 45 minutes to go to get some peanuts.
Okay, and don't send them by USPS. We still have that other guy in charge.
Or you can also leave the house, you know? Where are you now? Washington, D.C. or
I'm in Annapolis, actually, and I could turn my camera around and you could see snow on the top of my roof and my neighbor's roof as well.
Yeah, but you used to check around the world. You need to check around the world.
Texas, and I actually want to put my heart out to Texas. I was actually in communication with a student from University of Texas in Austin who hadn't had power for his house for 72 hours. And that's pretty rough in Texas. And my heart goes out to them.
Okay, so I just would like to remind people watching us here live on YouTube, Facebook, Twitch. At the archery. The landing is at 12:55 Pacific time. So we have some time still.
A little bit.
Well, thank you for joining us, Adrian. We really appreciated the overview of Mars 2020. And I know you have another event you have to attend that you are a very, very busy man today. So
yes, yes. And can I say go Percy? And also I'm starting to use go Ingi. Is that okay? It's very Australian to like just cut things off like that. But yeah, go Percy and go Ingi. Good luck.
All right, go
everyone.
Ingi. We'll make that happen. All right, Adrian, thank you again, and you have a good rest of the day, and hang in there, okay?
Thanks, Beth. Thanks, Brian.
All right, joining us next. Hold on, let me say, I just want to welcome a few people. So we have viewers watching from Chile, Moscow, Thailand, Nicaragua, Venezuela, here in the U.S. in Seattle, the U.K., India, Ireland, Mexico, Tennessee, Idaho, Texas. Please stay safe in Texas. Budapest, Italy, Washington, D.C., Chicago, Scotland, Norway, North Carolina, Florida, everywhere. Everybody's watching from everywhere. So we're going to bring on our next guest. So thank you to Adrian Brown. Coming up next, we have Dr. Janice Bishop, who is a scientist here at SETI Institute. She is a chemist and planetary scientist. She explores Mars through spectroscopy. Her investigations of CRISM data, together with spectroscopy of Mars analog rocks and soils in the lab, are revealing clays and sulfates in the ancient rocks that provide information about the geochemical environment at the time the minerals formed. And she's going to talk to us a little bit about the rocks and minerals at Percy's landing site, Jezero crater. So hi, Janice, welcome, and thank you for joining us.
Hello, Beth and Frank and everyone out there. It's great to be here. It's an exciting day. Every time we send a rover to Mars, it's an exciting day. So fingers crossed that everything goes well today. So.
Exactly. And so I'll ask you what I asked Adrian. Or how are you feeling? Are you nervous, excited, terrified?
It's always a mix of both. Yeah, excited, and then try not to think too much about what could go wrong, and just hang on and count down and hope all goes well. And we've had a good track record lately, but.
Right. We've had a good track record lately. Space is hard, though. So we just want to remind everybody that this is not an easy thing. We are landing a nuclear powered robot on the surface of a distant planet. And as the 90s proved, we don't always get it right, but we've been doing really well of late. So we're gonna keep our fingers crossed and our peanuts closed until such time as it's ready. So Janice, what are we looking for at Jezero crater? What have we got there? Why are we landing here?
Well, this is a crater lake like some of the other sites, but what is different this time is we're looking at some of the really old rocks on Mars. And the reason that's important is scientists think that in the earlier days, like 4 billion years ago, so a long time ago, that there might have been liquid water on the surface. And that liquid water is what we need in order to support life, whether it was on the surface or below the surface. Mars has dried up and the surface is really harsh and desolate and really not hospitable to life. And it's been that way for a long time. So what's new about Jezero is going to one of these really ancient sites where we have a better chance of finding biosignatures. And I can show an image here.
Yeah, absolutely.
Get this right. Here we go. So this picture shows a map of Mars. There are a whole bunch of little colored dots, and those colored dots represent a bunch of phyllosilicates, clays on Mars. And the more dots, the more clays. And right in blue, it says in white, it says Nili Fossi and Jezero crater. That's where we'll be landing. And then there's a blow up image of where the crater will be. And in black, I put the names of many of the other landing sites that we've been to already. And many of those other sites also found some clays, but we didn't see a lot of clays from orbit. We saw maybe a hint of clays or a small amount. And what's cool about Jezero is that we see lots of clays from orbit. And so I think we're going to see even a lot more clays when we get there with boots on the ground, with our rover, with our wheels on the ground to really test the rocks up close. I think it'll be really exciting to see that.
What does having the clays there mean? What does that tell us?
Well, the clays require water to form. And so having the clays means that there was liquid water. And Jezero crater, in addition to clays, also has carbonates. So on Earth, clays and carbonates are both often associated with life. And I'm going to show another image here. So this one shows, again, where the landing site is. So in the upper left, you see the crater, and there's a black box there. That's the region where we're hoping to land. And you can see the white ellipse. The ellipse is what the engineers use as their guide. They're shooting for landing somewhere in that ellipse. And one of the reasons we can go to Jezero crater now is that the engineers, every few years, they get better and better at their job of zooming in on one small area. And so it wasn't possible to go to Jezero before because we couldn't land with enough precision, but now we can. And so we're going there. And then the ellipse is near this delta region. So there's this blue patch of delta sediments. And then in the upper right image, you can see the different colors refer to different minerals. And so one of the questions we want to find out is, in this delta, did you just have ancient clays in the rocks that just kind of slid into the lake? Or was there enough water there for a long time that it actually altered the sediments and rocks and reformed those molecules and made new minerals? So we're going to be looking at the carbonates and the clays in particular to see, were these likely formed in the lake, or were they just kind of dumped in and rolled in when the water flowed in? So that'll tell us a lot about how long the water was there and what the chemistry of the water was, and if maybe conditions were right for life.
So is there one of these locations that you're like really excited to explore, and how soon will Percy get there?
Well, I think the rover first, it's gonna, once it lands, like Adrian said, it's gonna put out these navigation type cameras and try to check out where are we, because we don't know until the rover gets there and opens the eyes, then we'll see where are we and how close are we to that cool stuff at the delta, and kind of look around and then make decisions in terms of where to go. And when we got to Gale Crater, actually the scientists changed their mind a bit, because they were planning to just trek over to Mount Sharp right away, but then they decided, once they got the camera up and looked around, oh, hey, this looks kind of cool. And they ran more measurements than they had planned to at the actual landing site. So So we'll see what the first data show, and like any of these, you look around, you see what you see, you take a couple measurements and then make a decision. Is this stuff we're on right now pretty cool? Should we measure it some more, or should we head over to that delta that's really driving the mission? Trying to find out the main questions about the carbonates. Are they ancient carbonates in the rocks, or are they carbonates that formed in the sediments? And we may have both. It could be that we're going to find two kinds of carbonates. So we'll see what we find. It'll be really exciting.
So I bet you are incredibly excited about all of this, and it's really nice to have you here with us. And I hope you'll stick around and watch with us behind the scenes too. So
I'll be here watching and listening, and when we get closer to landing, if there's more questions, I'm happy to address those.
Okay, great. So Janice will be sticking around behind the scenes, so if we have questions, we will bring her back as we spend those minutes of terror between cruise stage separation and actual landing notification. So Janice, thank you so much for joining us, and we will talk to you hopefully a little bit later, and hopefully with good news.
Yes, I hope so. Go Mars.
Go Mars, go Percy.
Thank you very much. Can you hear me? Yeah?
Yes.
All right,
We
good.
hear you, Frank.
So now we have another speaker. We have someone from JPL, Elena. She has a PhD in planetary science and astrobiology. She's the science system engineer at JPL, working at the science operations as a science operation coordinator for the Curiosity rover, which is a rover currently on Mars in the Gale crater. So you are gonna, I would just want to mention that you were an REU, a SETI REU intern in 2008. So you work at the SETI Institute and you work with Janice, Dr. Janice Bishop in the past, and now you are a full-blown engineer at JPL. So congratulations. I'm glad to see that.
Former SETI interns unite.
Great.
So you're gonna tell us a bit more about how we operate rovers on Mars, because obviously it's not that easy. It's not like we're not remotely controlling it every day. So please.
It's not just a joystick. I've got a few slides that I prepared to share.
Go ahead.
Let me take over here for a second. Share my screen. Okay, and I wanted to just introduce myself quickly and talk about how I got this amazing job that I have, where I get to look at rover data every day, because I'm hoping that there's some students out there listening in that might get inspired to join a life of space exploration. So I consider myself a geologist. I am trained, as a hard rock geologist. I went to UC Santa Cruz, oh my gosh, 12 years ago. And as Frank mentioned, one of my first introductions to astrobiology was through the SETI Institute. And I was always very intrigued by SETI and the work that they did, thinking about if we're alone or if there's life out there. And I was given the opportunity to work with Janice and look at spacecraft data to think about, what do other planets look like? How do they compare to Earth? And, what can we learn from the rocks? So as I said, I'm a geologist and my expertise is very similar. I learned a lot from Janice and I really went running with what she taught me. So my expertise is, in mineral signatures and what they indicate about past habitable environments. What do they tell us about how the rocks formed? Could they have formed in the presence of water or environments that were or were not hospitable to life, etc. And I got to tell you, the life of a geologist is very exciting. You get to travel all over the world and get to go places that not many other people get to go. So I've been to Iceland and Hawaii and the Rio Tinto in Spain. And all the while I've been looking for, studying the rocks, studying what the rocks look like through instruments that we have on rovers and orbiters. And then, using that to piece together, how is the geology and the biology interacting with one another to tell us a story. And so I got that, that introduction at SETI, and I will forever be very grateful for my SETI family. And then in terms of what have I done since? So after my PhD, I went to Caltech for a postdoc, and I joined the Mars 2020 science team when I was there. And at that time, we were still choosing the landing site. So as Janice showed, there's some really interesting mineralogy that you see from orbit that point to this really exciting environment that was once there, this lake, and not just a lake, but a lake that, you know, could have also been just the right temperature and interacting with specific rocks that might provide energy for life. And then the sediments in the lake might collect those biosignatures. And so as a geologist, you take everything that you learn from Earth, and then you try to apply that to the limited data that we have for another planet like Mars. And so this was a really exciting time when we were doing the landing site selection, where all these Mars scientists from around the world came together and, you know, made their pitch for where they wanted to land the rover on Mars and why their spot was the best. And it was really exciting as an early career scientist to listen to everyone promote their site and advocate for their site. So in the end, Jezero crater was chosen. It's this amazing location, as everyone has talked about, with this remnant delta, and there was a lake there, and it could have supported life and also trapped life. And so you choose this site that really meets all these science objectives that the science team and NASA headquarters and all these people have laid out over the years. So with that, once now we have our landing site, we know where we're going to go. We're going to land that rover on the surface in, you know, an hour or so. And then what? How do the scientists, you know, meet their science objectives? How do we actually do the science on another planet? And that's where my current role comes in. I'm the science operations coordinator for the current rover, Curiosity. And so really what that means is that I'm the liaison between the scientists and the engineers, and I kind of speak both languages to make sure everybody is jiving every day, because it's a very quick turnaround to uplink a planet to Mars. So I'll start with, you know, when you're operating this $2.5 billion machine on Mars, there are a lot of things that you have to balance. You have to balance the science, you have to balance the science resources. So maybe you only have a limited number of cups or collection tubes for your samples that you have to be very careful with. And then you have to balance all the engineering resources. So how much battery do we have left? Do we need a recharge? When are our communication passes coming over? Are there pointy rocks that are going to eat our wheels and limit the lifetime of our rover? So there are many things that you have to balance on a given day. And so we have two teams. We've got our science team, and these are scientists from all over the world. Some of them are instrument PIs, some of them are grad students, some of them have competitively written proposals for what they want to do on Mars. And so there's the scientists, and they're all over the world. And then there are the engineers at JPL. And, you know, the role of the scientists is to, you know, make sure we are meeting our science objectives and really doing fantastic critical work on the planet with the data that we're collecting. And then the role of the engineers is to both manage the safety of our rover and also build the sequences and uplink those to the rover every day so that it knows what it needs to do. So how do we do this? As Frank alluded to, it's not just a joystick that we get to just immediately see, you know, with a video camera what we're doing on Mars. It takes, you know, the speed of light. It takes about 10 minutes, I think, for data to get to from Mars to Earth approximately. And so the way that we combat this is that we've got this cycle that we go through every day. So as a scientist, we wake up and we receive new information from Mars. So data, new images that the rover has taken. And we open our computers up and we get to see the first image straight from Mars, hot off the presses. Nobody else in the world has seen this surface of the planet at that same moment. And we quickly analyze the data that has come down from the night before. And the scientists assess it for, okay, what are we looking at? What does the chemistry say? What do the images, the morphology say? And what do we want to do next? What is the next thing we want to do? So first thing in the morning, the science team meets and starts building their plan for what they want to do that day. Do we want to take out our arm and actually look at the chemistry of the rock? Do we want to take really focused images across the crater? Do we want to just drive to our next location? So they have to figure out their science priorities, and there needs to be a science rationale for doing that. Once the science team has figured that out, it basically gets passed on to the engineers at JPL. And the engineers at JPL work to sequence all the codes. Okay, how do we move the turret in such a way precisely that it won't hit that little rock that might hurt the arm? Or how do we sequence and command the rover to turn the mast this way and drive 15 meters that way? And the engineers do that for a few hours across the day. And then, we go through many iterations of checking and making sure we're not going to accidentally bang the arm onto the ground, or making sure that we're actually getting the right rock that the scientists want, and not the one just over here, but the exact one that if you only have one chance to take the chemical measurement of, you're going to get it right. And so they build that all together, they bundle it up, and we send it to our ACE that uplinks it to the rover, so that the rover wakes up on Mars morning, receives its commands and says, okay, I know what to do today. Thank you for the instructions, Earth. And it does its thing while we're all sleeping here on Earth. It does its science, and then it sends the data back to us, and we start all over again in our cycle. And that's how MSL does it now after 8 years. You'll see with the Mars 2020 rover with Perseverance, they're going to be on Mars time. So they're going to be round the clock doing this. So this will happen in about 12-hour increments, where they'll receive the data, come up with their plan, uplink the next commands. With MSL, we've got it down to 8 hours. We've shortened down because we've been doing it for a while now, and we take weekends off at this point in the mission. And so my role as the science operations coordinator is to make sure that everybody is jiving, that we're really, everybody understands why we're doing what we're doing, and that we're going to do it right. And it's super fun. It's an amazing job.
It sounds amazing. I am envious a little bit. So I know we're running a little bit behind schedule, but I do have like one question. When you talk about sols, how do we measure those? I know Mars's day is a little bit different. So what comes up in that timing for you?
Yeah. So a sol is just a Martian day. And Sol 0 is the day that you land. So today is Sol 0 for Perseverance. It's really exciting. And then Martian day is like 24 hours and a handful of minutes. I don't have it precisely remembered. And so it's a little bit longer than an Earth day. But as you progress through the mission, you will, you'll be Sol 1, Sol 2, Sol 3, and so on. We're on Sol 3037 for Curiosity. It's pretty amazing.
So it means that the Mars 2020 team will have to adapt the time zone based on Mars. So they are going to be in a jet lag because of Mars. Every day they have to shift by 45 minutes because of the duration of the day in Mars. It's amazing. So soon you're gonna see zombies at JPL walking around, not because they travel through in different places, but just because they work on the Mars 2020 mission, and they change the schedule based on the daylight on Mars.
It's pretty amazing. The offices have blackout curtains so that team members can take naps under their desks if they're on, the night shift or not.
Great, thank you very much, Elena. We are running late, so we're gonna have to. But you staying for the rest of the show? You are going to be. I
actually have to leave because I'm going to go join some JPLers, with masks and socially distanced, but to, celebrate the landing.
Okay. Well, see you soon. See you again for one of our SETI Live for SETI Talk. Thank you. While I'm opening for the next speaker, Beth, can you introduce the next speaker? I'm going to invite him in the Zoom. Go ahead.
Sure. Our next speaker is David Deamer. His research concerns how protocell populations emerged on the early Earth and perhaps Mars. His approach involves polymerization and encapsulation reactions driven by wet-dry cycles in freshwater hot springs associated with volcanism. And with him is Bruce Deamer.
Hi, go ahead.
Hello, Frank, can you hear us?
Yes.
Yes.
Good. How much time do I have?
5 minutes.
5 minutes? That's just about right. Okay. I'm going to talk about one of the goals of Perseverance, which is to see whether we can find any evidence of early life on Mars. That has to do with this concept of habitability that Jim Casting came up with quite a few years ago now. And I'm going to add a new word that I just invented for this occasion. And the new word is originability. It's a little bit silly, but it does differentiate between the possibility that a planet is habitable, but may not have conditions for life to originate. And that's what we call originability. So let's think about that for a while. On Earth, we have extreme organisms, extremophiles, that can live in extraordinary conditions that we wouldn't think. I watched, for instance, a little microorganism swimming around in sulfuric acid from one of the volcanic islands near Australia, New Zealand. So life can adapt to extreme conditions, but that's no guarantee that those conditions allow life to begin. So let's think about Mars now. We don't know if it's habitable now. Maybe there's something alive there, but certainly we're hoping to find evidence of past life. But now let's think about the origin of life on Mars. We're going to add a couple of extra parameters to the definition of habitability. One of them is volcanism. Mars, and presumably the early Earth, had volcanic land masses. For the Earth, those would be coming out of a global ocean. For Mars, they would more likely be coming out of some land mass because the oceans were shallow and they didn't come anywhere near covering all of Mars. But nonetheless, there's volcanism. Now, here's the other thing I want to emphasize, and that is that ocean, salty water, is in fact an extreme environment for the sorts of biophysical processes that are necessary for life to begin, such as membrane formation. Membranes have a hard time getting formed in a deep brine with divalent cations like calcium, magnesium present. So what we now think is that if we had our choice on where to go on Mars, we might have chosen a place where we have already seen evidence for wet-dry cycles and hydrothermal volcanism. Now, my friend here, my colleague Bruce Deamer, was on an original committee for the Spirit rover. I'm going to invite him to say a little bit about what the Spirit rover found as a site that I sure want to return to if we have more Mars landings.
Yes, so Spirit discovered evidence of an ancient hot spring at Columbia Hills at home plate. And based upon this and evidence for the preservation of life in siliceous deposits that we find in the Pilbara 3.5 billion years ago, hot spring and siliceous preservation of stromatolites and even microfossils in the hot spring settings, an excellent preserver for biopreservation, that we feel that the Columbia Hills site, which I served as a member of the site selection team for Columbia Hills, would be a place in which we would not only have a potential for an origin of life in a hydrothermal surface hot spring setting, but as Mars lost surface habitability, the biota, or the basically microbial colonies that would be there, could escape through the plumbing into the refuge of the rocks. So we have a hypothesis called the first and last outpost hypothesis for life starting on a planet that's rapidly losing surface habitability. Its first outpost is actually where you can go and find evidence for past life. Why? Because there's evidence for water coming up, welling up to the surface of Mars fairly recently, within hundreds of millions of years, hot springs, siliceous deposits on the slopes of volcanoes, bringing up that biota in those brines. So we hope that at Jezero crater, if they can find any evidence for siliceous sinters there or hot spring influenced rocks there, they'll pay attention. And I think that the team led by Steve Ruff of the University of Arizona State did bring this to the attention, and so that was a consideration for the mission and the extended mission potential for Perseverance Mars 2020.
So, Bruce and Dave, what will be the consequences of finding life on Mars if we do find it?
I didn't hear all of that.
What would be the consequences for finding evidence for life on Mars?
What would I look for if I was looking for life on Mars?
Or the consequences of
The consequences of finding.
We did find a biosignature.
That's right. Yeah. Well, my goodness, that would be spectacular. The thing is that will let us know whether, in fact, life may have begun on Mars and was delivered to the Earth, so that we are all Martians. This is now being thought, pretty seriously by a number of our colleagues. Steve Benner, in particular, brought this up at a scientific meeting about 5 years ago. So wouldn't it be wonderful if life began on Mars and we are the outpost here on the Earth now? So that would be one of the implications for finding life on Mars, because we could easily detect if it was like Earth life, in which case that seems very reasonable that it began on Mars, or if it's completely different in terms of its genetic code and the chirality of the amino acids and this and that. There's a whole bunch of ways that we would be able to know whether it was a unique origin or in fact was being spread through the solar system.
All right. Well, thank you, gentlemen, for joining us. We're excited for you, excited to see where this research goes. And if you'd like, please stick around and hopefully we'll have some more questions we can ask you guys a little bit later.
Thank you. We'll be here.
All right. Wonderful. Okay, so coming up next, we have Joby Hollis. Joby is a postdoc and astrobiologist at JPL, where he works on the Sherlock instrument, the ultraviolet spectrometer that is on Perseverance's robotic arm. His work focuses on how we can use Sherlock to detect and identify the biochemical signatures of past life on Mars and figure out whether or not the planet could have been habitable in the past. Welcome, Joby, and thank you for joining us.
Thank you. First things first, can you hear me?
Yes, we can.
Amazing, great. Yeah, so thank you very much for that introduction. I'm a scientist at JPL, an astrobiologist, though I never actually studied astronomy or biology. I'm a spectroscopist by training, which is why I'm at JPL working on Sherlock. It is a spectrometer. It's one of 8 scientific instruments that Perseverance has available. And as you said, it's an ultraviolet spectrometer that is one of the main tools that we have to answer the question of, or at least one of the main tools this mission has to answer the question of whether or not life could have evolved on Mars, billions of years ago. The way we're going to do that is, as we're exploring Jezero crater and we are looking for, interesting rocks to find, if we find some of those like mudstones, that contain these clays or carbonates that were talked about earlier, that could have been made when there was flowing water in Jezero, we'll stop and we'll extend the robotic arm and we will deploy Sherlock, our spectrometer, to scan the rock with its ultraviolet laser. And we'll measure the light that gets scattered and emitted by molecules in that rock whenever the ultraviolet hits them. Now, every molecule generates its kind of own unique signature of this Raman scattering and this fluorescence emission. And so if we detect those signatures, we have a pretty good idea of what molecules are embedded in that rock. So in the case of like a mudstone that was produced when clay was formed from flowing water and then dried out as Mars dried out as a planet, then what we might be able to find are molecules that were embedded in that clay when it was deposited billions of years ago, when there was liquid water. And if some of those molecules are made up from like carbon and hydrogen atoms, what we would call organic molecules, well, those are potential building blocks of life. Life as we know it on Earth is made up from amino acids assembled together to form proteins. We're made up from nucleobases, which are small molecules that are assembled together to make DNA. So if we find those kinds of organic molecules embedded in those rocks, then we have an idea about the kinds of building blocks that were available for the possible formation of life in Jezero, in a place like Jezero crater, billions of years ago when there was liquid water, when we think the planet may have been habitable. And what's more, if we find complex structures made from those molecules, so if we did find something, akin to DNA or protein, we would be able to observe that complexity in our Raman and fluorescence spectra from Sherlock. And you know what? The first thing we would do if we found something like that would be what Adrian was talking about, which is we would immediately take a sample of that rock, store it in a tube, leave it behind for a future sample return mission to pick it up, bring it back to Earth so we can study it in more detail.
So, in your personal opinion, what do you think are the chances that we find traces of life?
I don't know. I don't think I can make an educated guess on that because we have so little information to work with, right? We only know of life existing in one place. That's Earth. That's a sample size of 1. We don't even really know how to fully define life at this stage. So we're really not sure what we're looking for. And so guessing the probability that you might find something, well, I feel like we're just setting ourselves up for disappointment there. But I believe that we're looking at a place where we're fairly confident that there was flowing water in the past because we can see evidence of this river channel, the delta it formed when the water flowed into Jezero crater. We can see these marginal carbonates and these clays that Janice was talking about that were produced when that water slowed down and deposited the minerals it was carrying. As far as we're aware, based on what we know of life on Earth, that's a great place for organic material to assemble and potentially assemble into complex structures that could potentially become a living thing. So hopefully these rocks that we're going to look at with Perseverance and with Sherlock will be giving us our best chance to find that evidence we need to establish whether or not those processes really happened on Mars billions of years ago.
Wonderful. Thank you,
Thank
Joby,
you very
for
much,
being
Joby.
with us.
Are you staying with us for the rest of the show? Yeah?
Yes, I will. I'll be here to answer questions.
Okay. All right. We will take some questions later on. Thank you. The next speaker is Pascal Lee, planetary scientist at the SETI Institute and the Mars Institute and NASA Ames Research Center. So his research focuses mostly on the moon and Mars, especially on water, ice, and the cave that you can find there. He has 30 years of experience in field works. He travels around the world, Arctic, Antarctica. He's looking for Mars analogs and moon analog as well. Very fascinating life, by the way. So I don't know what you're going to talk about, Pascal, but you have 5 minutes to tell us everything about exploration of Mars you're faced with. Exploration of Mars, humans versus robots.
Yeah, well, hi, Beth. Hi, Frank. Thank you for having me. It's a great, by the way, great event so far. It's a big day for us, right? Because any day where we have a Mars landing is a big positive event. So I'm really happy about this. I just wanted to follow up on a few points that were made earlier about the meaning of finding life on Mars, and where this mission fits in our big picture of the search for life. I continue to well, I still think that a mission like Perseverance is, of course, very important to pursue and important to carry out. But in a real sense, that no amount of fossil finding on Mars will really tell us if we have found what we really want to find, which is an example of alien life. You could imagine Perseverance finding a sort of a road cut with fossils jutting out at you, okay, and finding evidence for carbon, hydrogen, that there was life on Mars. We still would not know if we're dealing with alien life or not. And as we know, Mars and the Earth are not closed systems. Planets exchange material through natural processes. We have meteorites that have come from Mars naturally. The planet Mars gets impacted by asteroids and comets. These larger impact events eject rocks that travel through space. Some of these rocks fall on the Earth. We pick them up. They are meteorites. We have in our collections today over 200 meteorites that represent different locations, essentially, from Mars. And you know, this is very this has very profound implications. It means that life could have started on the Earth. The Earth as well was impacted by large asteroids and comets. Earth rocks could have traveled to Mars. We could have seeded Mars with Earth life, and vice versa. Life could have started on Mars, seeded the Earth. We could all be descendants of Martians. This was a point made earlier. But the key thing, though, is that in order to determine whether life we find on Mars, even ancient life, in this ancient water setting in Jezero crater, to determine that if it's alien or not, we would really need to do genetics on it. And you cannot do genetics on fossils. You have to find life that was either living or dead for not a very long time, not long enough for the organic genetic material to be affected, altered by radiation, by decay, by later reactions. And so this to me emphasizes the need for us to really transition our focus from what we've been doing so far, which is to look at Mars's distant past and the environments that were suitable for life in the past, where we've established that there's been water for a long time near the surface of the planet, to a strategy where we're actually going after places where we might actually find life today. Because only if you find life that is still alive could you do genetics on it and then establish that the genetic signature of that life is radically different from that of all life on Earth. All life on Earth shares a lot of profound commonalities in our genetic makeup. We're all part of what's called the tree of life, the tree of Earth life. What you really want to find is an example of a life form that does not fit onto that tree. So I think we need to do deep drilling on Mars, because by accessing the underground, you will have a chance to access environments that are more suitable for at least Earth-type life, more shielded from radiation, more wet, warmer settings. And drilling, of course, is the hard way to do it. Another much easier way to access the underground is to go into natural caves. And we now know of over 1,000 natural pits and caves on Mars, where I think we should really focus our attention on, especially the ones that are on the flanks of some of Mars's giant volcanoes. These volcanoes could still be active, even though they're not erupting now. They might be just dormant, not dead. And so I have a lot of hope for an exciting prospect for a new phase in our quest for life on Mars that would focus on looking for life that's still alive today. Now, do I still have time to talk about humans versus robots?
Yeah, but quickly.
Okay, humans versus robots. It's actually not a real competition at all. What robotic exploration allows us to do is to start answering very important scientific questions we have about Mars and other worlds. And of course, sending robots is a lot cheaper and a lot less risky to Earth, to human life, than to having humans out there. But the truth is, the history of exploration or of human space exploration has nothing to do with a competition between robots and humans. It's not like there is a point where robots could not do any more exploration and somehow it would be time for humans to take over. That has never been the place. We can continue exploring Mars for centuries to come with robotic means, and I believe we will. The time for humans to go has nothing to do with that. Humans go into space for things that have a much bigger dimension than just collecting scientific information or exploring a place scientifically. Science is a big component of why we would send humans to space. But sending humans to space has a dimension that has to do with expanding the realm of human activities, of human presence. It's inspiring it's a driver of our technology. It's inspiring for education. When you look back at the Apollo program, there were three big benefits to the Apollo program. One is, of course, it allowed the United States to defeat the Soviet Union technologically, because the Soviet Union was ahead of the US at the time in space endeavors, at least in terms of doing a few firsts. And so by putting a man on the moon and returning him safely to the Earth, that was some way of really establishing, that you were very capable as a society and as a technology to do these kinds of things. So that was gain number one, beat communism and the Soviet way of life by establishing that, the American and capitalist way was able to make big achievements in space as well. The second big reason, of course, was science. We certainly learned a lot about, the moon. Before we had Apollo, we weren't quite sure yet whether all these craters on the moon were impact craters or volcanic craters. And so we've learned a lot about the bombardment history of the solar system, how planets formed. There was a big scientific benefit, of course, to sending humans to the moon. But it wasn't the reason why we sent humans to the moon. We didn't send humans to the moon in the mid-60s just because we all of a sudden became curious about the origin of craters on the moon. We did that primarily because it was imperative to catch up and beat the Soviet Union in the space race. But the third most important reason, really, that has yielded maybe the biggest benefits to any society that has invested into sending people into space is the fact that the Apollo program excited and inspired an entire generation of young people to go into science, technology, engineering, and math fields. I often refer to this plot from the NSF where you show a real spike, a doubling of the number of people in science, technology, engineering, and math as a result of this Apollo inspiring endeavor. And so to me, the time for humans to go to Mars is when we will realize it's of strategic importance for the nations who will undertake that to understand the benefit that it will bring to inspiring a new generation of people to go into science, technology, engineering, and math, to stimulate the spirit of exploration in humans. And it has really nothing to do with competing with robots. You can always design a robot that will be more specialized and do things better than humans in particular ways. Sending humans into space themselves has more to do with the aspiration of our existence as human beings and our connection to the cosmos.
Fabulous, Pascal. Wow,
Pascal,
thank you.
Pascal has a meeting at 2:20, so I don't think we have time to take questions. But are you coming back after?
I'll try to come back closer to the 7 minutes of terror.
Okay, thank you.
I'll add to the terror. Thank you, everybody. Bye-bye.
So up next joining us now is Casey Moore and Stephan Hunker. Casey is a space environment specialist at Maxar, where he studies the impact of hostile environments on spacecraft integrity. He trained as a planetary scientist, studying the atmosphere of Mars using images from Curiosity. And Stephan is currently the mechanical engineering manager at Maxar Space Robotics, where he has worked for about 5 years. He works on engineering systems for harsh environments, including subsea, terrestrial, and now spaceflight hardware. Stephan and a small team of talented technical personnel developed the SHA for the Perseverance rover in close cooperation with JPL and are excited to see it put to work. Welcome, gentlemen. Thank you for joining us today.
Thanks, Beth.
Thank you for having us.
So, you're going to talk a little bit about exploring the Mars surface with a rover. What sort of engineering difficulties, things that you had to work on to make this happen?
So I'm going to defer to Stephan, considering he led that project. So,
sure, I'll talk a little bit about the sample handling arm and its capabilities. We call it SHA, so you'll hear me refer to it as the SHA affectionately a few times throughout what I'm going to tell you guys. But you don't often see the SHA on the rover in some of the stock images that you see on NASA's and JPL's websites, because the SHA is actually tucked into the underbelly of the rover in an area called the ACA, or Adaptive Caching Assembly. So the SHA's purpose in life, it's a 3 degree of freedom robotic arm, which means it's got three joints of motion. So there's a vertical translating, we call it the Z stage joint. And then there's 2 anthropomorphically named rotary joints that we call the shoulder and the elbow, after their likeness to the human body joints. And the SHA's purpose in life is to take these critical soil and rock samples that some of the other guests have spoken about and pull those through the out of the bit carousel and then move them to different stations within the rover. Inside the ACA. Those include a vision assessment, station, volume assessment, seal station, a hermetic seal dispenser, and also a tube storage station, for example. I think the mission goal is to have a minimum of 20 soil or dirt and rock samples to be stored, and then hermetically sealed for a subsequent sample retrieval mission that people have also alluded to. So the SHA is a small arm with a big job here. It's kind of the last point of contact with the sample tubes prior to storage. To give you a little bit of idea of the size, it's about 16 inches tall, 20 inches long, and it weighs about 34 pounds. You see a lot of the videos on YouTube. It may seem like the SHA is moving quite quickly. That's not actually the case. Normally, the videos that are showed are with the SHA sped up, because it would be a little bit boring and make for a long video if it wasn't. But the Z stage, for example, moves at about 0.5 millimeter per second when it's coming close to the station interactions within the ACA. The rotary joints move at about 0.05 RPM, so those are also quite slow. I think at this point, so I don't take up all the time, I'll share a quick couple of pictures here, and then I'll hand it over to Casey, and he can talk a little bit more about the planetary science.
Great.
So this is an image of the what you call the adaptive caching assembly, and specifically a component called the CCMD that you can see right here. Kind of mounts. Let me make this a little bigger. Mounts inside the rover chassis. This is actually the sample handling arm. This is the sixth such robotic arm that Maxar has designed and built for Mars service, and it's one of the most complicated. Picture doesn't really do it justice, but you can see some of the major components here. The Z stage moves vertically up and down. This is a bellows assembly here to seal out dirt and rock to protect the internals of the mechanism from some of the harsh environments that it's going to see on Mars. And then you can also see the rotary joints, one of the rotary joints here and one of the rotary joints down here. And then we've got the end effector, which is where the actual interfacing with the sample tubes happens. I think I've got one more picture here where you can kind of see up here, this is what the sample tube looks like. And these in the background are all the different stations and some storage areas over here. So essentially the SHA, or sample handling arm, that Maxar has built here is designed to move these sample tubes around to these various stations on the underside of the rover, and then store them for that subsequent sample return mission. And Casey, you want to talk about some of the planetary stuff?
Stephen, quick question. How deep will the rover take samples from? So how deep can that dig down?
I'm probably not the best person to answer that question, honestly. I'm a mechanisms guy. The scientists tell me how deep we need to take these samples from, right?
Okay.
So I'll defer to them.
All right, Casey, what have you got for us?
Hey, so I didn't come with slides, I'm sorry. That's okay. So I was hoping you or Frank would have something to ask me, or I don't know, what are we discussing?
So Casey, you work on the Curiosity mission. Can you tell us a bit what you did while you were working on this mission? What specifically was your...
So I was
an engineer or what?
I was on a part of the science team. And so I had a role of science operations planner. So essentially, whatever the atmospheric scientists wanted to study, I would help plan that schedule for the rover. And so we took a lot of images of the sky to get how much aerosols or dust are in the atmosphere at Mars. And so a lot of my work dealt with radiation. And
so you were not interested in the rocks, you were interested in the atmosphere.
No, we were not. We were atmospheric.
Okay, sorry, you were looking up with the rover, or you were looking down with the orbiters?
On the rover, we were looking at the sky.
Okay.
Yeah.
Yeah, some of us have seen pictures taken by the rover when you see a sunset and sometimes the moon, Deimos, and Phobos. So you were part of this team working on this specific data?
Yeah. So my specific data was looking at the crater rim. So that was something that was 20 kilometers or so away. And using those images, I was able to infer how much dust was in the air within the crater. And so this is a data set that we can get from looking straight down from orbiters. But it's really hard to get estimates for low-lying dust because the crater geometry blocks this point of view from an orbiter. And so finding a way to do that with a lander was kind of critical to get like the low-lying dust within the crater.
So are you, for both of you, you work at Maxar, it's a private company. And that's one of the reasons I wanted you to be part of this as well. It is because most people think that the JPL or NASA is building those spacecraft, but no, in fact, they're made of pieces from an industry behind it. And the reason in the US we can develop this kind of rover and launch them on Mars and land them on Mars and operate them is because behind there is private company that has been working for years on the technology capable of doing this. So Maxar is one of the contractors. They have the arms in Perseverance. For how long Maxar have been working on Mars rovers or Mars orbiters? Do you know?
Well, I can chime in and say that we've supplied all of the robotic arms that are currently on Mars and operate in various stages of operation and performance right now. So it predates my engineering career a little bit, but for quite a while, I think it's safe to say. So this will be the 6th such arm that Maxar Space Robotics has built for JPL, and I think we've got a really talented team here in Pasadena is where we do our mechanisms designs, and we're all super excited about this. We've got a socially distanced gathering later today to actually watch the touchdown coverage. So we're excited.
All right, thank you. Are you staying for the rest of the landing? It's the separation is literally in 10 minutes. The cruise separation.
Sure.
Okay. Turn off your camera and let's see David. You want to do the introduction, Bess, while I'm preparing the rest? Go ahead.
Sure. All right. Thank you, Casey and Stephen. Joining us now are Troy Hudson and David Stafford. Troy's role as an instrument systems engineer, coupled with his background in planetary geology, has served him well as he led the 2-year effort to address the penetration anomaly that faced InSight's heat flow probe, the Mole. As that saga draws to a close, he looks back on the challenges of being on Mars and having to do things you never planned for. And David was the mechanical ground support engineering lead for the Mars 2020 Alto Assembly Test Launch Ops. While on the Alto team, he wore a lot of hats, and his primary role was support and development of all the mechanical support equipment that was used to build Mars 2020. Welcome, gentlemen, and thank you for joining us today. How are you feeling? Are you excited? Are you nervous? Where are you at right now?
Oh, incredibly excited.
So Troy's gone through this. This is my first. So a lot of feelings and emotions.
Yeah. So a little over 2 years ago in November of 2018, InSight landed, and that's a mission that I had worked on for nearly a decade at that point. And as many of you know, InSight faced quite a few challenges when it arrived, particularly with respect to the Mole, which is our drill that was designed to penetrate into the subsurface to measure planetary heat flow. I have a few slides to show you, so I will share my screen here, and then we'll turn it over to David to talk more about his experiences on 2020.
Okay.
All right, I hope you can see that screen now.
Yes.
So you'll see in this lovely image that there's the InSight lander with the seismometer, which is listening for Mars 2020's Perseverance's arrival in just a few moments. And on the right-hand side, you see the Mole drawn here penetrating into the subsurface. But that's not how it worked out in practice. When we started the initial digging, the Mole stopped. And there was a large effort over the last 22 months to try to understand what the issues were. And we had to make do with the resources available on Mars, the robotic arm, the cameras that we had. It wasn't a lot to work with. And everything that we did on Mars, we first had to test on Earth you never want to do something for the first time in an environment like Mars. You want to have practiced it. So on the lower right of this slide, you see myself and my colleagues, Ashite and Christina, in the test bed at JPL, practicing one of the key maneuvers we did, which was to lift the support structure out of the way of the mole, revealing it and helping us better understand what the problem was and how we could assist the mole. So we practiced that many times at JPL before moving on to doing it for real on Mars. And so here's the comparison from some tests in our test bed lab on Earth in Pasadena, California, and then the actual motions that we did with the arm to assist the mole on Elysium Planitia on Mars. We had some successes. We were able to assist the mole, as you see in the images on the left. We got it to penetrate deeper into the ground. There was no rock blocking it. We made progress. And then the unexpected happened. In the same configuration, you see in the images on the right, the mole backed out of the ground. It was an almost catastrophic moment of unexpected behavior that we then needed to use the resources we had and recover from. We did, and we were able to further assist the mole by doing some more risky maneuvers, pushing on the back cap close to the tether, finally getting it fully buried so that it could serve as a probe of regolith thermal properties, the thermal conductivity of the soil. So while the InSight mission as a whole has been incredibly successful, it is a further emphasis to all of us that Mars is full of surprises, and the amazing robots that we created to do these explorations, they have to solve the problems with the resources they have. And I'm hoping that Perseverance encounters very few of those problems. And David, I would like you to go ahead and talk about your work on 2020 and how critical it was for what we're about to see.
Well, thanks, Troy. Yeah, so as Ari said, so I was the mechanical ground systems lead for 2020, and what that sort of comprises of. There's a lot of ground support and basically large hardware that's required to sort of build the spacecraft. And so kind of what I'm showing here, this is our SAF, this is our spacecraft assembly facility. This was right sort of at the beginning before we went to the first round of environmental testing. And in this high bay, yeah, you see what's almost assembled spacecraft for the first time, what we call during stacking. But this is a large high bay, but you see all this tooling, all this support structure, carts, systems, and there's a ton of tooling out in the airlock and sort of out and about. And so it takes a lot of hardware to build a small spacecraft. This thing is on the order of about 10,000 pounds. We shipped and we utilized well over about 100,000 pounds of just hardware. So part hardware from a mechanical and both an electrical standpoint. So this is a busy high bay, and then we had to reconfigure this high bay. And this whole high bay here, we had to move. When we went from JPL to Kennedy, we had to pick up this entire high bay and then literally ship it across country. So that's a lot of stuff to ship. And so what I wanted to show is there's a lot here to comprise to sort of build Mars 2020 with Perseverance. Just before we did this, I was also in the role of sort of environmental testing. And after we just finished the first spacecraft stack, we went right into the first round of sort of environmental testing. Here you see on the left, this is acoustic testing. This is where we simulate the acoustical energy that's seen during launch loads. And as I show you about some more interesting hardware, yes, we see Mars 2020 here, but here's in this spacecraft transporter, and you also see the DT and PLA, the payload launcher rack, if you will. And so it's a lot more tooling to sort of get this. We had to move the spacecraft on lab, and it required a whole different sort of transporter system that we had to design and develop.
Because these test facilities are physically separated from the high bay where the spacecraft is assembled. And so you have to move all of that stuff out in the open.
Yeah, we're down. We literally have to go up a hill. I mean, JPL is not exactly level ground, so you have to literally climb up a couple hills and then maneuver this thing within with inches of accuracy. And so, as you see on the test on the right, this is a more sort of advanced test. This is the thermal vac test. We had to finish acoustic, go all the way down the hill, take the spacecraft and flip it, and then we had to then get it ready for thermal vac. And to even get this into our chamber, which you don't see here, massive amount of tooling. It took large ramps, a whole new floor. a large dolly that comes in here, and then we literally have to jack the whole system up in order to get it to its 6 suspension cables. And so at this point, you see here, this is the final product just before we go into thermal test. The technician looking at the work we've done. The solar sun is activated. So this is a fraction of the energy that you see from the solar test. And this just shows you just how much tooling is involved to sort of get this small spacecraft into our largest chamber on lab.
How long did it take you to get that thermal vac setup created?
So we were able to sort of base off legacy MSL hardware, but you're talking well over 6 months to a year out. We're doing planning and hardware development, refurbishing hardware to make sure everything still works. And so we had 2 teams working in parallel, setting up hardware, while the ATLO team was down in the bottom of the hill, setting up the spacecraft. And so we had to be working simultaneously to work, sort of keep our launch schedule. After we were done with environmental testing, oh yes?
Gentlemen, sorry to interrupt you. In 1 minute, we have the stage separation. Can we just see it on the screen, Beth, quick before, and we go back to you, just to see this? Because we cannot postpone the stage separation.
No, absolutely not. We want to see it too.
Beth, you ready? Let's Beth share a screen, please, and then we go back to this. So just to explain, the spacecraft is not flying directly to through space. It's basically, he has this kind of a spaceship that is attached and helping for communication and guidance, etc. So what's going to happen now? The spacecraft is coming close to Mars, and it's going to basically split with this attached spaceship called I don't know the name of it. And we're not going to see it live, but we will see videos rendering of it. Beth, you ready? Can you stop the screen, please? The share screen. Thank you. All right, we have the subtitles. That's great. Can leave it the subtitles. Perfect. We don't see your screen, Beth. All right.
Just the eyes on the solar system showing separation.
Oh, there we go.
Well, we missed it, Beth. We don't see your screen. All right. Can you explain this, maybe, David? Better than me, probably.
You're talking. Oh, so yes. At this point, we're going to start well, we're not quite EDA yet. That's about 10 minutes from now. But what'll happen? We're at a spin rate. So the cruise stage now separates at this point. We're still spinning. So we're going to eventually go through a D-spin. We'll go from about 2 RPM to about 0. And then we also have to start to jettison the cruise masses as well. So as one of my fellow engineers, one of the other mech leads, Emily, who was the cruise stage sort of cog, she's seeing her work for the past 5-6 years now be dead weight and fly off, basically to burn up in the atmosphere.
The cruise stage has done its job.
It's done its job.
It got it there with solar panels and communications, and now it doesn't get to land.
Nope.
At least not in one piece.
But it's gonna crash. It's gonna crash somewhere on the planet. So maybe we find fragments one day or another, right?
Well, it's designed to be so we don't have to contaminate the surface. So the entry atmosphere will be able to burn up successfully. So we don't add our own contamination.
Okay. So apparently NASA announced that they confirmed the separation was successful. So I remind people that what you're seeing here, it's not a picture of what's going on in space. It's a rendering. And this happened in the past, in fact, because the separation has happened. And the time we get the message that it's been confirmed is only now.
There's about an 11 1/3 minute delay from where Mars is to Earth for light communication right now.
So for sake of simplicity, we're going to assume that we are seeing it live, okay? Even though we know that we are seeing the past here because of the time, the delay to get the information. I discovered yesterday how they do this kind of messaging with the spacecraft during the entry. It's in the first phase now, in fact, now the separation happened. The spacecraft is not capable of communicating with us with a very high bandwidth. So they send what they call tones. They predefine some kind of radio signals, which can be combined, like the key when you play music. And that's from these tones, they know the state of the spacecraft. They kind of basic information, such as I'm still alive, I'm starting the...
Moving at the speed you expect, that sort of thing.
Yeah, exactly. It's kind of interesting. Now we are in the phase where basically the spacecraft tell us some very simple information about its state based on tones, based on music. It'd be great that one day we get this complete information and someone make maybe some cool music from that. Do you want to go back to your presentations? I'm looking right now. So the 12:39.
Yeah, we have about 7 minutes until the entry interface starts.
Okay.
So we've got a little bit of time.
Yeah, we'll go back really quickly, and then we also want to celebrate and watch too, because we've literally got 3 computers in here with different live feeds, from all the teams, since we're complete virtual at this point. So sure, really quickly. Kind of going back a little bit. So I was also the transportation lead, and so that was a new challenge. I've never done logistics. I mean, it's a little bit more than just ordering from Amazon Prime, if you will. And so it kind of fell on my shoulders. To move Mars 2020, Perseverance, it took basically a small army to go from JPL facility in Pasadena all the way to the Kennedy Space Center. And so all totaled, it took a total of 3 C-17 aircrafts, 1 KC-135, about 24 Pat semi-trucks full of hardware, and a small army of both military and of civilians, all working together with a common goal to get Perseverance, Mars 2020, across the coast. And so you see here, we fill these airplanes. These are very large containers, and from the left side, you see the descent stage. Up on the top, you see the adaptive caching. That was a complete separate assembly that came later, that we integrated into the rover much later due to cleanliness requirements. And you see on the bottom right, it took a team of us, and no one was afraid to do pushing and labor to go to get that rover off the airplane. You see all of us there at the bottom, pushing the container out to get it back to the forklift, and then to get it off to our packaging and assembly facility after that. So,
and you did all this during COVID.
Well, this is the start of COVID, and so COVID had kind of just started, right when we did the rover transports, we started getting more familiar with COVID. March Air Force Base, where we flew out of, had a containment unit that we kind of was aware of, and we're like, wait a minute, what's going on? And so yes, we did the transport just before all so this is early February. Everything sort of changed right around mid-March when Florida and California started shutting down. That changed all of our operations basically for the rest of the at-load period while we're in Kennedy.
Yeah. Big challenges.
So then finally, so after we got to Kennedy, we did a lot of sort of the final integration work, a lot of mass, a lot of weights and measures, and do a lot of balancing. We do what's called the final spacecraft stack. And so ultimately what you're seeing, how do we get the rover now packaged up into the big conic section that you sort of see as the spaceship that's flying towards Mars at this moment? So what we do, it's a set of spacecraft stacking sequences. We literally take the descent stage, we attach it to the top of the rover with the separation bolts, and that becomes what you see here, the powered descent vehicle. We then take the back shell on its tooling carts. This is a lot of GSE you see here. We fly it over the powered descent vehicle, and then we slide what's called a PDV outrigger underneath it. And we literally, with the shell over it, we literally pick up the entire powered descent vehicle and then stuff it up inside of the aero shell with very, very, very tight precision. This is probably one of the heaviest lifts we do. This is about a 12,000 pound lift, all trying to put delicate hardware within millimeters of other hardware. So this is probably one of the most delicate, probably high intensity actions that we do. Once we do that completion, we have the back shell now made with a PDV on the bottom left-hand corner. It scarf its big rotation vehicle fixture. We then take that whole conic section, and we then lift that whole thing up before it meets the cruise stage. And as you see, this is the last part where we don't have the heat shield installed yet. This is just about the last phase where we do the closeout. This is kind of some of our few last chance opportunities to sort of do anything left with the vehicle. Once we make the heat shield, we literally pick it up, attach it at the separation points. We rotate it over, and then we do what's called the final lift. And so as you see here, the final spacecraft hoist, this is just after fueling, and you see it's kind of complicated to be able to grab a 15-foot diameter, spacecraft. And so you see a lot of tooling, a lot of sort of big hardware had to be used to sort of do this. And so with a finesse and a very dialed in team, we do the last lift to the PLA, which is the payload launch adapter on the bottom right. And that's sort of our handoff. And so our closeout to where we hand off to ULA. And we're saying, all right, you now got our spacecraft. Let's get to Mars safely now.
So this is EDL in reverse, but in a very delicate and deliberate way.
Yeah, you'll literally see this fly in reverse as we go through the next, about EDL in the next 7 minutes. You'll see the reverse of this pretty quickly if all goes well.
So we only have a few minutes left. We did want to turn it back over to you for your program.
Could you stop the sharing? Thank you very much, both of you. You stay with us, please.
We'll do what we can. That was me when InSight landed on November 28th. David's reaction shot has yet to be filmed.
So you don't have a T-shirt for the special occasion for this one, right? I'm noticing this.
But he's got.
Oh, yeah, this is the landing team. Yeah, this is the landing photo that was going. So we.
Oh wow! Keep that because you're gonna be able to sell that on eBay. It's gonna cost a fortune in the next 5 years.
Heck no.
Yes. Can you start sharing the screen of the NASA? Yeah. Thank you. We are going to be entering soon in the atmosphere, right? Can you explain to that, Beck?
We're about a minute and a half from entry interface, which basically explained on the NASA feed, which is why I'm going to basically give this back to you, is an arbitrary point above Mars where we consider it the edge of the atmosphere. So that's where the Perseverance craft, as it is right now, is supposed to hit that atmosphere. And right now what they're doing is they're keeping track of these heartbeat tones that they're receiving from Perseverance. Basically, that tells it it's still there.
We should explain that the spacecraft is screaming into the atmosphere right now. It's not like an airplane. It's like basically going to 12,000 miles per hour, entering in the atmosphere. So because
we're sending a giant bullet at the surface of Mars.
Exactly. And because of the speed, of course, there is a heat coming by friction. So what you can see, we're starting with the peanuts. No, that's chips. As you can, so to protect the spacecraft is equipped with the heat shield that you have seen in the presentation from David. And this heat shield will protect the spacecraft from the heat and protect the interior as well, and also protect from vibration. I think we need to start the tradition of the peanuts, because if there is no peanuts, this is not gonna work. Maybe Bess, you can explain the peanut story.
It's a long-standing JPL tradition. I even have forgotten how far back it dates. I don't know if David or Troy know the answer to that, but when I first did Curiosity, that was when I learned about it.
Oh, it goes back to the Mercury and Gemini and Apollo programs. It's a long-standing NASA tradition.
We have confirmation of entry interface.
Good. So this started basically the official 7 minutes of terror, right?
Yeah.
So that's the slowdown. The deployment, it will be followed by the deployment of the parachute, which will be at 12:52 in 3 minutes. So something also very interesting is that every time we launch a spacecraft on a planet, we learn. So in fact, we talk about the heat shield as something that protects the spacecraft, but it also contains a lot of sensors and captors that measure temperature, pressure, vibration, and they collect those data. It's called, the instrument is called Medley, if I remember. And Medley is collecting data at the moment. And the reason JPL is doing this is because they want to learn how to send spacecraft on Mars, because in the future, we may send human beings as well. So we need to collect data now while we're doing it with robots. It's less risky. And so we learn a lot from Medley 1, which was on the Curiosity rover. And now we have Medley 2, the instruments, the set of sensors on Perseverance. So for instance, one engineer told me at JPL that during the landing of Curiosity, they noticed some anomalies. And one of the anomalies was the fact that the wind was stronger than expected. And that's one of the reasons Curiosity did not land exactly where it was supposed to. It was slightly shifted. It was not that big, but they learned from Medley 1. So they hope that the landing for Medley 2 will be better. And we have multiple reasons to think that it will be better in terms of landing exactly where we want. I'm going to go back to this later on. So where are we now? 12:51. I noticed that we have people still connected here, our speakers. So if you want to join us, please join us. Just
feel free.
Just start your camera and you will pop up on the screen automatically. Joby, Janice, Casey, and who else is there still?
We're about 16 kilometers up. And the heading alignment is set. So we're no longer trying to change things up. We're just going where we go now.
Exactly. Yeah, I should mention that during this phase, there is some kind of rockets on the top that align slightly the heat shield and the spacecraft. So the position is optimal and the location as well. So now it's truly a bullet. There's nothing we can do until the deployment of the parachute.
They've already stated it's reached maximum deceleration, so. We're 15 kilometers up. Still receiving signal just fine.
So the next step is a parachute. So the parachute is there. Go ahead.
This is cool. This is the maneuver that I have abbreviated as SUFR, and the actual acronym spells out to straighten up and fly right. Parachute has deployed.
Okay, but that's the critical part. As the spacecraft is still twice the speed of the sound at the moment. With the parachute deploy at subsonic, is going to basically go to subsonic speed. This is one of the, I think this is the largest parachute ever built for this kind of mission.
We're now down to subsonic speeds. Heat shield has separated.
Already, wow, it's accelerating. Yes, true, 1252, 5239. So this basically, they jettison the heat shield because they don't need it since we have a lower, the speed is significantly lower now. So the speed should be something like 160 miles per hour, which is still significant. And now we're gonna start the time where we do the TRN. So what is TRN? TRN is terrain relative navigation. So that's a new thing, in fact. Curiosity didn't have that. I'm speaking fast here because I know it's gonna be super fast. So TRN is basically, we activate some camera and sensor and radar, and they look around and they analyze the terrain in real time. This is entirely robotic, nothing, no human intervention here. And this TRN basically decide, this is where we're gonna land, because that's less risky because there is no cliff, there is no crater or no rocks. So
we are about 4 kilometers up now.
4 kilometers altitude. Okay.
And the lander has produced a valid landing solution.
So that's what I meant. The computer on board finally say, okay, we're gonna land here. Let's hope it's a good choice. But we should always trust computer, right? They're never wrong.
Back shell separation confirmation.
So this is the back shell, which is the, I always forget exactly the use of the back shell, but this is the thing that was stabilizing basically.
We're a kilometer up.
1 kilometer above the surface. You know, I barely see what's going on my side here.
300 meters.
So now we have deactivated the small rockets on the side to slow it down even more. And the next step is the separation, the sky crane. So we're gonna see a picture of that very soon. When is that? I should have seconds on my computer because obviously I'm lost here.
Sky crane maneuver has started. 20 meters up.
So this is the risky part where we slow down the spacecraft to the point, and when we deploy the wheel and we wait, we stabilize it, we land it, cut the cords, hopefully, and jettison the upper part. And it's done. Apparently,
Touchdown confirmed.
Maybe
Crack
the
out the
before.
peanuts, everybody. We did it.
Hi, another lander on Mars. It's always easy when you look on the computer, right? So we don't have the sound here, but obviously, as you can see at JPL, they're extremely happy about the success of the landing. But not over, because now we know we have landed on Mars. They will basically inspect and check if everything is right, if the wheels are deployed, if the instruments are working properly, the state of the spacecraft, if it's straight, tilted. There is a lot of things that's gonna be
Still
done
getting telemetry, so we're still good.
So it's still alive. That's what I meant when I say we still getting telemetry. It means that the spacecraft is sending data. So the way we get data at the moment is using one of the orbiter. We can listen to the rover.
Yeah, the Mars Reconnaissance Orbiter and Mars Maven were both receiving signals from Perseverance as it was going down.
Perfect.
And now we're going to see if they're going to see if they can get some images from the rover.
Yes, so just before the landing, there is some cameras on the side that may have taken a picture and may have been able to send the image to one of these orbiter. This is not mandatory. That's something they would like to have because they swear they ensure that the spacecraft has landed in proper position. So let's see if we get this picture. It's not going to be a pretty picture because it's a picture taken with the lens cap. So it's going to be blurry, but if we get a picture, even a blurry one, we know that the lander is, the rover is in good state.
They're applauding again because they're still getting a signal. So they like the confirmation.
Still alive. Any comments from our other viewers here? Troy, David, you seem very happy.
But all I care about is my mom and sister.
Say again?
You seem very happy.
Yeah, you have a smile.
Oh, yes.
Smile.
You have no idea.
Is it $2.5 billion or it's just because it's alive?
Sorry, you're not coming through clearly. We've got a lot of feeds going on here.
I'm sorry. It's because it costs $2.5 billion and now it's on Mars, so it's because you're excited by the space mission and the future of the space mission.
Well, this starts, Mars sample return. There's a lot of other projects now, hinging on this. And so my next path is, Europa Clipper. That's my next path. But most of my team is on the sample return project. So that just secured a whole lot of new future growth and the chance to bring a sample back. Yeah. This was the linchpin. This had to happen in order for return to happen.
Despite how sophisticated the instruments are on Perseverance and Curiosity before it and InSight, there's a lot you can't do on Mars. You need laboratory facilities on Earth. And so bringing a sample back from Mars, particularly from a site as interesting as Jezero, is the major next step in our, increasing our scientific understanding of Mars.
Writing on this.
So we have a new visitor, Bill Diamond. Bill Diamond, the CEO.
Perseverance is alive.
Bill, you're live.
Of Mars.
Bill doesn't know he's live.
Hi, Bill.
Bill, you're live.
Welcome
Hey,
to our live
guys,
stream.
hold on. I gotta switch the screen over. Here we go. Let me turn the sound off on the other website. All right, can you hear me?
Yes,
yeah, we can.
hear you.
Great.
Welcome.
I've been going back and forth between our coverage and NASA's coverage and playing a little Zoom ping pong here. But wow, how exciting is this?
Oh wow, yeah.
So Bill,
I'm sorry,
maybe
I'm not going to be. Go ahead.
Is there any involvement of the SETI Institute in the Perseverance mission? Maybe kind of a summary.
I don't have all the details of our involvement in this mission. Unlike Curiosity, where we had an instrument on board, the ChemMin X-ray diffraction system, we don't have an instrument payload on Curiosity, but we have scientists, of course, working on the project. mostly in terms of, awaiting the mission data, both in terms of visual data and of course, analytical data from the onboard instruments. I don't know, Janice may be in a better position to talk about some of the specific science that we're going to be doing for the mission. And if Nathalie joins us, hopefully she will, she can perhaps offer some insights as well.
I'm just going to share my screen really quickly.
So Joby, Janice is here. Janice, can you tell us the step for you as a scientist? Now we have a Perseverance mission on Mars for the SETI Institute.
Well, it's really exciting that the landing worked out, yay! And we'll have a spectrometer on board, not the visible near-infrared spectroscopy that I primarily use, but Raman spectroscopy. And Pablo Sobran from the SETI Institute is working on that, and we'll see what the Raman spectrometer can tell us. We should be able to find out what kind of minerals are present, and also find out about the organic molecules in the soil or in the rocks. So that'll be interesting to see.
I think that's the main thing. The Raman spectrometer will be able to detect as any organics that it might come across, right?
Definitely looking for that, as well as the mineralogy, to try to piece together the history. All we can see is what's there now. So we look at the clues that we can see, and we try to put together the history back in time to 4 billion years ago, when liquid water was present on the surface, and when the whole planet of Mars might have been more amenable to life.
Janice, maybe you can talk. I
So
think probably some of the other...
Joby,
hold on a sec.
Yeah, Joby is a postdoc at JPL. Joby and astrobiologist, and he works on Sherlock. So Joby, you have a job for the next 10 years now.
Well, yes. Unfortunately, I'm only at JPL for 1 more year, but it's going to be very exciting because, for one thing, I'm on the mission operations shift starting in a few hours. So we're going to be looking at some of this data that we've got back from the rover, and we're going to be planning the test activities that will be taking place on Sol 1 tomorrow. So yeah, this is incredible. I couldn't turn my camera back on too quickly because I was just having a little cry. Such like a moment of like tension being released. It's just fantastic.
There's live images already showing up on the Mars site. It's fantastic.
There is some picture taken from the side camera.
Front and back.
Front and back cameras.
Yeah.
Hey, Nathalie.
These are engineering cameras. That's amazing. I mean, not only we have pictures like seconds after she lands, but then she knows exactly where she is.
That's
just... So don't worry, people, we have not been photobombed. This is Nathalie Cabrol, director of the Carl Sagan Center at the SETI Institute. Sorry, Nathalie, I was just about to introduce you.
Sorry, so, I'm excited.
No problem. Everybody's excited. That's great. So we have a first picture of the Perseverance mission here. As I say, but hey, it's
a little hard to tell anything from those images, except that the rocks look flat, which is good news.
Maybe you could explain why having rocks flat is important for people like you.
Also, Nathalie, as part of that, I think it'd be great, particularly from your perspective and Janice's and Joby's, to talk about the significance of the Jezero landing site as a site selection.
Yes. Janice, do you mind if I go first and then you?
Go ahead.
Okay. So many moons ago, we advocated for impact crater lakes on Mars because the first, when we only had Viking mission data, the impact craters were the only thing we were sure were holes in the ground. And when you were seeing valley networks converging towards them, we're pretty sure that water ponded there. And when we're trying to advocate for lakes on Mars, these were pretty sure things. So this is why, and they are good things exactly for, all the explanation you've heard today. Lakes are wonderful places for life, for recording as well, seasonal changes, climate changes. So it's an amazing place to learn about climate and also good environments for life. So that's no surprise if NASA has sent 3 out of 4 rovers in impact crater lakes. First one was QSEP, and then came Gale, and now we have Jezero. Jezero is an amazing place. It's probably in my mind the previous one were all wonderful, and Gail is wonderful. In terms of scenery, I think that Jezero is going to be incredible, but in terms of keeping the record of the environment and having a chance to see how fast it changed and how habitability might have changed and the type of environments for life and microhabitat it could have provided, I think this is the best place of all. So flat rocks, because usually when you deposit sediments in lake, they are going in stacks. And then when they are going and they are eroded, then what's left are, pancake, flat, stacked rocks. Janice?
Oh, thank you to.
Yeah, I would say this
Janice.
is exciting going to Jezero because we're getting sort of a look back in time. The other sites were a little more recent, so that we're looking at a lot of ancient sites on Mars, but this one is 4 billion years old. So we're, instead of looking at something 2 or 3 billion years old, this time it's really much older into Mars's past. And on Earth, of course, our planet has changed a lot in the last 4 billion years. So it's really hard to find any rocks that are 3 or 3.5 billion years old. So here on Mars, we're luckier in that extent. And so we get to look at the ancient rocks at Jezero and try to see what really happened 4 billion years ago. What was the extent of the liquid water, and how did the minerals form, and what kind of chemistry was taking place? And were there organic molecules there? Did they react? Were they just organics that were distributed probably everywhere in the solar system? Or did these react together to potentially form the molecules needed for life? So hopefully we'll find out some of that on this mission.
And Janice and Nat,
Okay,
maybe you can
we're
also
gonna-
both comment on your backgrounds, because they're also relevant and intriguing.
Okay, well then I would say that what you have behind me is probably one of the very best example of terrestrial analogs to a place like Jezero crater. This is in the Andes, and this is where me and my team, including Janice, have been working for the past 5 years now. So, and this tells you a lot about how to search for life, for microbial life in extreme environment. This is the main lessons, and why we were going there, to try and understand which type of instruments and what kind of strategy and methodology you need to use to find life. I just would like to comment a little bit on what Janice said about the ages of the various landing sites in the past for the rovers. They are not that young. Gail, in fact, is 3.8 billion years old. Gusev is 3.9, but what Jezero has is that it covers really that time where Mars was habitable to the point where she transitioned into being a planet that's the planet we know today, cold and dry. So with Jezero, we are going to, it's like opening a book of stone and peeling the layers of time, exactly like Janice said, and learning how fast and how deeply Mars has changed.
Okay, thank you very much. We are going to end pretty soon this live SETI live. You'll be here for like 1.5 hours. Thank you for everybody you here is coming to tell us your thoughts. I'm pretty sure we are going to have a lot of conversation on the Perseverance mission, on Ingenuity in the next in the future. We have a SETI live, our SETI talks. In fact, our next SETI talk will be about Mars 2020. So we're gonna talk about science with this rover and invite some of the scientists who are involved in the mission. You can turn off your camera. Thank you very much. Bill, see you soon at the SETI Institute. Nathalie is the same, and Janice as well. Bess, it's all yours.
Thanks, guys.
Right,
Take care.
Thank you, Bill. Thank you for joining us.
You bet.
Thank you, everybody else, for joining us, for all of our watchers on Facebook and Twitch and YouTube. We appreciate that you spent this significant chunk of your day with us, and congratulations to NASA Perseverance and their various teams. Thank you for the donations that were made across our social media. We really appreciate it. And Franck is hosted at the Archery, which is a shared workspace in the Mission District of San Francisco. that houses a public cafe, an exhibition space, and supports a community of entrepreneurs, makers, and artists. Also, we'd like to give special thanks to the production members, Pocket Pictures, for their AV support today. The event gives the opportunity for members of the public to be part of this landmark event, and we are hugely, hugely appreciative that all of you chose to spend your time here with us on our feed. So thank you very much to all of our guests for joining us. Thank you for all of your questions. And thank you for everybody who's watching. Thank you, Frank, for setting all of this up. Frank did like most of the legwork here today and did an amazing job. So thank you so much for all of that.
You know, Bess, you've been doing a lot too. This is a good teamwork. So thank you also to Rebecca and Lee and Barbara that you don't see. They are in the back, making sure that everything works and the technology is with us today. The technology was with us for the Mars landing. It was also with us for the SETI Live, here at the archery, and at the SETI Institute. So thank you very much, everybody.
Yeah, thank you. And don't forget that tomorrow we will be back in the morning with a special live grudge report for those of you who are fans of our show. And we will have Dr. Erin McDonald here with us. She is the science consultant on the Star Trek series. So come join us tomorrow morning. We'll be on again at 11 a.m. Pacific. So see you guys then. And thanks for watching.